Okay, let's talk about intermolecular forces. So, intermolecular forces are attractive forces between atoms and molecules. And these forces, the reason that they exist, or the reason different molecules and atoms attract one another, is due to partial charges. Okay, and the larger that partial charge is, the stronger that intermolecular force is going to be. And the closer the charges can get, the stronger the forces will be. Um, and so the partial charges, how big they're going to be and how close they can get is all affected by the size of the atom or the molecule, the structure, so what it's actually, made up of, and the shape of that, and the polarity. That all impacts, your partial charges in the molecules and atoms, which are going to control how strong those intermolecular forces are. Um, and the reason we would care about this is because it impacts several things. So one thing is it impacts the physical state of a substance. Okay, so that's why some things are solids and some are liquids and some are gases. Now, of course, we can take a solid and we can heat it up and melt it into the liquid phase, or we can take a liquid and heat it up and vaporize it, or we can do the reverse processes by taking heat away. But at a given temperature and pressure, the reason something is in a particular phase is due to the actual forces, the attractive forces between the molecules or the atoms. Okay, so the intermolecular forces involved. Now, the stronger those forces are, the more restricted the motion is going to be. So if these particles, if these individual particles are strongly attracted to the others, it slows them down. It doesn't let them move as much. Okay, meaning you are leaning more towards being a solid, because in a solid phase, things are kind of fixed in place. Whereas when you have weaker forces, it's less restricted, meaning the molecules or atoms, they can move more freely, meaning at that point they're going to be in the gas phase. Now, the reason temperature would affect that is because if you increase the temperature or decrease the temperature, you're changing the kinetic energy. So you're putting more energy in, allowing more motion. Okay, so you're actually giving them enough energy to overcome those attractive forces. Okay, and so that's why you can force it from a solid to a liquid to a gas by increasing the temperature. So those intermolecular forces are still there, particles are still attracted to one another, but if you give those particles enough kinetic energy, they can kind of break free of one another. Um, Now, another thing that's really important that intermolecular forces impacts is different physical properties of substances. Um, and so there's lots of them. We'll just look at some. I just want to list a few. And so melting point and boiling point, those are really important characteristics of a substance. And really the reason things have different melting and boiling points is because they experience different attractions between the molecules. So different intermolecular forces. Their strengths are different. And so that causes the melting points and boiling points to be different. Another thing is the density. The reason things pack tighter or looser has to do with how they're interacting with other things. Um, Things like viscosity and surface tension for liquids, so how well a liquid flows or how um, easily the surface can be broken, depends on the interactions between those particles that make up that substance. A couple other things, solubility and hardness, that's all tied to intermolecular forces as well. So how much interaction or how strong those attractions are is going to determine how easily you can break them free of one another to dissolve them, or how easily you can kind of break apart a solid. Um, and so there's lots of reasons we would want to know about intermolecular forces. Okay, it can help us make predictions about substances, and predictions how one substance might be similar to another, or one substance might benefit us because it has a higher melting point or higher boiling point or something like that, just by understanding a little bit about the structure of the substance and being able to predict intermolecular forces. That can help us make predictions about macroscopic information, okay, these macroscopic physical properties that we care about. So let's talk about the different types of intermolecular forces. We will focus on London dispersion forces, dipole-dipole, and hydrogen bonding. Those are the ones that would generally be clustered under van der Waals forces. Those are the intermolecular forces that are involved with covalent compounds, okay? When you have ionic compounds, there's some additional types that involve ions, of course. We're not going to talk about those. Um, it comes up a little bit when you talk about solutions, but in general, the most useful ones are going to be the ones that relate to your covalent compounds. So that's what we're going to focus on. Now, London dispersion, sometimes people just call them London forces. Some people call them just dispersion forces. And any of those are perfectly fine. So London dispersion forces, these actually are experienced by all molecules and atoms. Okay, so no matter what the substance is, they always experience London dispersion forces. Um, these are the weakest type of intermolecular forces. So it does cause an attraction between these atoms or molecules, but it's a very weak one. But this type does occur in all of them. And we'll talk more in detail about what exactly a London dispersion force is, but I just want to give you the overview first. And then we have dipole-dipole forces. That exists in polar molecules. So remember I said London dispersion is for everything. Okay, so whether or not it's an individual atom or a molecule, and whether that molecule is polar or nonpolar, it does not matter. Everything has London dispersion forces. But dipole-dipole is restricted to polar molecules. Um, and then hydrogen bonding is kind of a special case of dipole-dipole. Okay, it's actually a very strong dipole-dipole. It's when you have polar molecules that specifically have either an HN bond, an HO bond, or an HF bond. And these are going to be the strongest out of these three, okay? If you added in the ones that are associated with ionic compounds, those are actually even stronger than these intermolecular forces. But like I said, we'll stick with covalent compounds at the moment. And so we'll just go through these three in more depth. And so if it helps you to think about this a little more pictorially, you can kind of talk about it in terms of this diagram. If you've got this big circle that encompasses everything, that would be London dispersion forces, and then a smaller portion of that would be the polar molecules, and that has dipole-dipole forces, and then an even smaller chunk within that has hydrogen bonding, and that's because they have those particular bonds in those molecules. Okay. Now, one other thing that you need to realize is intermolecular forces. That's an interaction from one molecule to another or one atom to another. So the individual particles that may have interactions within them, those we're not talking about. We're talking about those particles now interacting with another particle. And so those interactions, those attractions are much weaker than what we call intramolecular forces. And so the intramolecular forces are the actual bonding forces. So those are your covalent bonds and your ionic bonds. Okay, so covalent bonds and ionic bonds are within a molecule. Okay, and so those are really strong. The intermolecular forces, that's just a slight attraction between the molecules. Okay, so these two different things. The the bonding forces are kind of what controls the reactivity of things, the chemical reactivity, whereas the intermolecular forces, that controls the physical properties of things. Okay, um, so let's talk about each of these in a little more detail. So London dispersion forces, that is an attraction between temporary dipoles, or we can call them instantaneous dipoles. So remember, a dipole is when you have this substance, this molecule, and it has kind of a partial positive charge on one end and a partial negative on another end. Okay, so it has this dipole. Um, and so that occurs in polar molecules, but also in nonpolar. But when it occurs in a nonpolar molecule, it's only a temporary dipole. So it's not something because of what makes up that substance. These temporary dipoles are actually, something that, as it says, get formed temporarily. But remember, this is experienced by all atoms and molecules, okay? But the temporary dipoles are just really a fluctuation in the electron distribution of the atom or the molecule. So when we have an atom or a molecule, if you have an atom, you have a nucleus and you have electrons around it. Okay, you have like this electron cloud around it. If you have a molecule, you have several nuclei, and then you have electron clouds around each one of those. So there's essentially a big electron cloud for the molecule. Okay, and that electron cloud, it's not fixed in place. So the electrons that are there, they're not fixed in place. They can move around. Okay, so what happens is, at certain instances, you can have the electrons be somewhat distorted to where they're kind of heavy on one side of the molecule, okay, or one side of the atom, to where there's more electrons over there. Okay, so just in the motion of this. So at different instances, there'll be these temporary dipoles or instantaneous dipoles that get formed. Okay, and so that forms a dipole that then can interact with other things. So if we're talking about individual atoms, we can have these individual atoms, and usually we'd think we have a nucleus and then we have this nice spherical electron cloud around it. But that's not 100% true. There's constant movement throughout that, to where at different instances that cloud can be kind of distorted towards something else. Okay. And so then you have kind of a partial positive on one end and a partial negative on another end of that atom or molecule. And those partial charges will then attract the partial charges that an adjacent atom or molecule has temporarily. Okay, and that interaction from one molecule to another of their temporary charges, that's the London dispersion force. So it's not anything to do with what's going on inside that molecule. It has to do with that molecule interacting with another one. Okay, and it happens because of these instantaneous dipoles that form at different times. Okay, so it's constantly fluctuating, it's constantly changing. Now, London dispersion forces, we say those are the weakest, but you have to be careful. You can have London dispersion forces in, two different atoms or two different molecules, and one of them is stronger than the other, even though overall they're considered to be the weakest. That's because it's only temporary. But you can have, one atom has stronger London dispersion than another. And what controls that is what we call polarizability and the surface area of whatever you have. Okay, the more polarizable something is, the stronger London dispersion forces it's going to have. And what that term means is that it's more easily, or the electron distribution is more easily fluctuated. Okay, this is going to happen when there's a larger electron cloud. So if you have larger atoms or larger molecules, they have more electrons, thus a larger electron cloud. and so it's more easily distorted. Okay, and so the London dispersion forces would be greater. Okay, so sometimes to estimate polarizability, we look at mass. Okay, it's not perfect, but in general, if you have an atom that has a greater mass than another, then the one with the greater mass is usually more polarizable. That's even more so true for molecules. Okay, for atoms, that can trick you sometimes, but for molecules, for sure, as you have a larger mass, it's pretty much a guarantee that it's more polarizable. Okay, that it has a larger electron cloud. And then surface area would just have to do if you have, larger molecules, of course, okay, with respect to either you have more atoms in this, so it has a larger surface area, or if you're talking about, say, organic compounds, where you have these carbons attached, you can have, say, one where these carbons are in a ring, so it almost creates a blob, whereas another one maybe has the same number of carbons, but they're in a straight line. And if that were the case, then the ones in a straight line have overall a greater surface area, so they would have stronger London dispersion forces. So those things impact the strength of the actual London dispersion force. Now, let's talk about dipole-dipole forces. Those are an attraction between permanent dipoles. So it's different. You have London dispersion, that's a temporary dipole. So that's temporary, just fluctuations in the electron cloud that cause these partial positives and negatives that are there one instant and they're gone the next. Okay. So they're constantly changing. So even though there's this attraction, at this instant, then there's another new attraction in this instant, since it's constantly changing, it's weaker. But in the case of dipole-dipole, there's a permanent dipole. So there's a permanent partial positive charge on one part of this molecule and a permanent partial negative on another part of that molecule. And what happens is that fixed partial positive and that fixed partial negative charge is going to attract other opposite partial charges. Okay. And so this is going to be experienced by all polar molecules, because polar molecules are the things that have a permanent dipole, or a net dipole, you can also call it. So any polar molecule has dipole-dipole forces. It also has London dispersion. It's just the dipole-dipole are stronger, so that's usually what we're focused on. But it doesn't mean the dispersion isn't there. The dispersion is still there. This is, of course, caused by permanent dipoles. So, of course, that's why it has to be a polar molecule, because that's the thing that has them. But these permanent dipoles, like I said, the opposite charges are going to attract one another. But it's between two molecules. So you have these two polar molecules, and they'll line up to where the partial positive of one of them is aimed at the partial negative of another. Okay, and so that attraction between those charges, that's what we're calling the dipole-dipole force. And when you have this large sample, you'll actually have a lot of these interactions. Okay, it's not just two molecules, it's in the entire sample you have this going on. And so, as I was saying, yeah, the opposite ends of the dipoles attract. So partial positive end attracts the partial negative end, and that's favorable interaction. So it kind of holds those things together a little bit tighter than the London dispersion forces. So the interactions of those temporary dipoles. Now, hydrogen bonding, remember I said, is just a very strong dipole-dipole force. Okay, so that's going to be experienced with any molecule that has an HN, an HO, or an HF bond. Okay, and they can have more than one of these as well. Okay, so it doesn't matter if it has at least one of those bonds, then it's going to have hydrogen bonding. Now, this can be in really large molecules where you just have one of these bonds. Well, then the one portion of the molecule that has that one bond can hydrogen bond, whereas the rest of the molecule may just have dispersion forces if it's nonpolar. And so it just depends. So there's some examples here when you have water. So H2O molecules, of course, have OH bonds. So water molecules can then interact with other water molecules. And so what would happen is the partial negative oxygen end of one water molecule would interact with the partial positive of another water molecule. So the hydrogen end, okay? And there's lots of them that will interact with multiple molecules at once. But the key is it's always the opposite ends, the opposite charged ends will want to interact with the others. Some other common examples, HF, so hydrofluoric acid or hydrogen fluoride gas, that can have hydrogen bonding because you have the HF bond, and the F end is partially negative, a large partial negative, and the H end is a partial positive. So then, of course, they want to interact with their adjacent molecules. And then ammonia, NH3, is another common one that has hydrogen bonding. And even if you mix those things, so say you put ammonia in water, then the NH bond of ammonia can interact, or the dipole of the NH bonds can interact with the dipole of the OH bonds from water. Okay, so you can have hydrogen bonding between different molecules if they both have the components necessary. Okay, but you can have within that same sample things hydrogen bonding themselves as well. So really what's causing this is those bonds, the HN bond, the HO and the HF, those are really, really polar bonds, okay? Because H has a really small electronegativity, whereas fluorine and oxygen and nitrogen all have very high electronegativities. And the reason they're high is because they're very small atoms, meaning those electrons are getting really close to the nucleus of those atoms, and that's where the positive charge is. So they have a very strong pull on those electrons. Okay, so, oops, that was the last one. So that's the basics of your intermolecular forces. As I said, there are more kind of classes of intermolecular forces. There's mixed forces, and there's ones that involve ions. But this is a good start, and this is where we'll focus for our intermolecular forces, at least at the moment.